So thank you for introduction, and thanks to the Samir and Sujay for inviting me to have talk here. And today I want to talk about a little bit different topics, but closely related with mock modular form. So I think the origin of this workshop is this function. This is a Q series, and the observation by Eguchi, Oguri, Tachikawa is that these numbers are closely related with the dimensions of irreducible representations of M24. So the mathematical fact is that H tau is mock theta functions. It means under the S transformations, this transform like this one. So this is not modular, but in the terminology, this is one of mock modular form, and the weight is 1/2. So we call this H is mock theta functions. So thanks to the discovery of Tsubeigas, we know how to complete the modular properties of H functions. It means if we add some functions to H precisely, then this H hat recovers a modular property. This means under the S transformations, it behaves like
eta cube of Z.
Mm-hmm.
Eta cube of Z.
Eta cube.
In the eta cube of Z. So which are integrating that tau?
Yeah. Sorry. Yeah.
No,
Okay.
right,
This one.
No, sorry, it's my fault. I think I just didn't read it correctly. So
Are
that's
you?
The integration.
Yeah. Okay. Sorry. So this is one of mock theta functions, and my topic here is to claim that similar objects of with this H function appears in quantum invariant. I mean the quantum invariant of not or three manifolds. So in this context, this is called mock modular form, but recently Zagier defined another terminology. He defines a quantum modular form. Here, quantum does not mean that the argument is not non-commutative, but this is closely related to quantum invariant. So this is so Zagier called quantum modular form. Anyway, so we give a definition here. So quantum modular form F is a function of rational to the complex number, and such that for all gamma, I mean this gamma is any subgroup of SL to D. Then H gamma defined by this one. Has some properties of continuity or analyticity. So this is the definitions by Zagier, but you know this is very flexible one and not mathematically established one.
So what is chi?
Chi is some multiplier, depends on gamma. Okay, so in the modular objects has this term must vanish, but here this is a very flexible definition. So mathematically not established one. So I want to talk about this quantum modular form here.
The usual modular forms are not even well defined on the
Yeah. So yeah. Okay, so anyway, I studied on modular form based on this quantum invariant. So I want to explain my motivations.
Sorry, can you expand on that question or remark about why you start with Q? Why
This one?
Yes, why did you pick Q?
So I want to explain why we have interest in Q. So anyways, this is just a definitions of flexible definitions of quantum modular form. So yeah, anyway. Anyway, so I want to explain why this quantum modular form is is very interesting to me. So my background is conjecture from the quantum invariant called volume conjecture. This is first proposed by Kashaev around 95, and this is still open. So the claim is that so this is a claim of volume conjecture. So I will now explain the notations. So here K is a hyperbolic knot. So later I will explain what is hyperbolic knot. But anyway, please regard K denotes some knots in three sphere. And then Kn is Kashaev invariant, depends on knot K and natural number n. And later, Kashaev originally defined Kn based on the quantum dilogarithm functions. But later, it was realized that this K coincides with Carrado-Jones polynomial at specific values. I mean, the Q, later I will explain what is Carrado-Jones, but anyway, the Carrado-Jones is mathematically well established ones, and Kashaev invariant is identified as a special point of the Carrado-Jones polynomials. So this is due to Hitoshi Murakami and Jun Murakami. '99. Okay, so anyway, to understand the left-hand side of Carrado volume conjecture, I want to explain the Carrado-Jones polynomial.
Sorry, what is the meaning of the right-hand side?
Later I will explain. Yeah. First, I just want to try to explain the left-hand side. So Jn is just is called Carrado-Jones polynomials, and to construct the quantum invariant of knot, we use a braid group constructions of knot K. And I mean the important relations in braid group is just these relations. I mean, sigma I is just a change of two strands with ith point, and I plus 1 point. And then the left-hand side is this one, and the right-hand side is this. So you know that this is trivially identical. And to construct the invariant, we want to have representations of sigma I. And this relation is for physicists. This can be well understood from the relations of scattering matrix. We omit R, but from the integrable system, these relations can be regarded as the Yang-Baxter equations. So the solutions of these Yang-Baxter equations is well established from the framework of quantum group, and the most famous one is Jones polynomial. And in that case, as examples of solutions of these braid group relations, we have 4 times 4. This is just an example of R matrix. And when we use this R matrix, we can construct Jones polynomial. This explanation is very rough, but anyway. And this Jones polynomial corresponds to the large N is equal to 2K. I mean, each strand has two dimensions. So this R matrix has 4 by 4, is 4 by 4 matrix. So this N Carrado-Jones polynomial is given as a generalizations of Jones polynomials. So this is the definitions of Jones polynomials. Okay. So we know the R matrix. So we can construct the quantum invariant by using this braid group representations. So as an example, we study this knot. This has 4 crossing. So as a conventions, this knot is denoted as 4-1. Okay, so we know the n-dimensional representations of R matrix. So we can construct the, we can calculate the quantum invariant for this one. But generally, it's possible, but the form is a little bit complicated one. So the most difficult one is to collect terms together and obtain very beautiful explanations. And in this case, it is known. The Collard-Jones polynomial.
This expectation value in UN Chern-Simons?
So SU2 Chern-Simons with n-dimensional representation. And here I use the conventions of Q analysis. Xn means a product of this one. So I express the Collard-Jones polynomial as infinite sum, but this large n is positive integers. So at finite small n, this vanishes due to this one. So we write as a infinite series, but the anyway, this is just a polynomial of Q and Q inverse. Okay, to see meaning of volume conjecture, although I do not explain the meaning of right hand side. Anyway, we explain, we compute the left hand side. Okay. So the Kashev invariant is a special value of Collard-Jones polynomials. So we substitute Q to the n root of unity. Then the Kashev invariant is just given by this one, just a real number. I mean, omega is nth root of large nth root of unity. So we want to let's calculate the left-hand side. So to this purpose, we understand the summand can be written like this one. So we want to study this asymptotics. Let's study these functions. I mean, functions of n. I define Gn like this one. Okay, it is easy to see that this one has a graph like this one. And at k equal to the n over 6 and 5n over 6, this equal to unity. So from this picture, it is easy to see a behavior of this Gn. And first, this sign is smaller than unity, so this decreases. And then this is a very rough estimate, but it is easy to see that at the n, small n equal to the 5n over 6, this Gn takes a maximal value. So, so we know this Kashaev invariant is estimated in between this one. So this is a very natural estimations of Kashaev invariant. So we take we compute the large n limit of this one. So by this, by taking large n limit, it is easy to see this one coincides with this limit.
Gn is when the picture is bounded by some positive value, so how can the sum over n from 0 to infinity converge? This is Gn that you just
This is Gn.
And you're summing Gn from 0 to infinity, right?
Sorry. Very sorry. Sorry. Because omega is just nth root of unity. So if we if small n is larger than large n, this vanishes.
So then the last inequality is probably n times g of n over 6 rather than.
Yeah.
No, the last inequality that you wrote doesn't quite make sense to me. N times.
This one? Okay. So we have.
The left hand side. How does it? I thought it would be.
This is always positive and just take n summation, large n summation. So
It will be n times gn by 6.
That's what I would expect, yes.
n times.
The lower value is n by 6. It's g of n by 6.
It is always take a sum of these values. So this one is always positive. So it is always larger than this value. Okay. Okay.
The lower bound is that if n equals 6, the very first term, g of 5n over 6.
Yeah, the lower bound is.
Shouldn't it be g of n over 6? Because that's the lower bound of g of function of.
So I think at least at one point it's g of 5n over 6.
Yeah,
Right? So that,
it's just when n is large,
Yeah.
you have a term which is g by 1 over 6.
Oh,
Just
One of the terms is g of 5 over 6, so since the sum is positive, it must be that.
All right. Okay, from these definitions,
How did it become equality?
Because large n, log n over large n vanishes. And for 1n is always positive, so and this is just from definitions of G, and then finally we obtain this one. Here, lambda is Lobachevsky functions. So anyway, in the case of 4, we can compute the left-hand side. So I want to explain what is what's the meaning of right-hand side. So I want to explain what is hyperbolic volume. I mean, if mathematically it is known that the complement of hyperbolic knot can be constructed by gluing hyperbolic ideal tetrahedron together. I mean, the as a gluing of ideal tetrahedron. So the ideal tetrahedron is, I mean, the three-dimensional hyperbolic planes, hyperbolic space. The shape of ideal hyperbolic tetrahedron is like this. I mean, the 3 vertex is on the complex plane, and the remaining 1 vertex is infinity. And in the here we consider the 3-dimensional hyperbolic space like this one. And it is known that the hyperbolic tetrahedron has a shape like this one. And here, we have a usual Euclidean triangle here. I mean, this is same with this one. And in this space, geodesic is just a hemisphere. So the bottom one is just a surface of sphere. So the hyperbolic volume is just a sum of this hyperbolic, sum of volume of this hyperbolic ideal tetrahedron. So to do this, as the metric is like this, so the volume of this tetrahedron is just a
What is ZI? Is it some cross ratio?
sorry, so I will explain. Yeah, cross ratio, but just a moment. Anyway, from this matrix, the volume is given like this one. So we can compute exactly this one, and we know the result is just a sum of Lobachevsky function. And here, alpha, gamma, beta is dihedral angles of this triangle. I mean, only depends on the dihedral angles. And the sum of alpha, beta, gamma is just pi. So, and the metric is scale invariance. So the important fact is that this function, this sum of three Lobachevsky functions can be written as one function, d is z. Here, z is just, we assume in complex plane, this three coordinate of three vertices are 0, 1, and z. So alpha, beta, gamma is determined by only from a unique complex number z. And dz is called Bloch-Wigner functions. Bloch-Wigner. Bloch? I don't know. Li2 is dilogarithm functions, and take an imaginary part and with some additional terms. So anyway, the very rough explanations, but any ideal hyperbolic tetrahedra is parameterized only one complex number. So as a totally as a volume of not complement, just take a sum of each volume of each tetrahedron. So that is the definitions. So to check this volume conjecture is correct for one case, this number must coincides with the hyperbolic volume of complement of for one case. So I explain the case of for one. And this case, it is known that the complement of this for one not case is decomposed into two hyperbolic tetrahedron. Two hyperbolic tetrahedra. I wrote this tetrahedra, but the meaning is the same with this one. And we orient, we give an orientation of each edge and label each faces BD, and this is A, and bottom is A. So to construct the knot complement of this figure 8 knot, we glue faces together, same faces with the same label together, and orientations of edge must match. I mean, if we glue this B face with this one, so we gave orientations of each edge, so it's uniquely determined how to glue faces together.
Just a question. What exactly do you mean by S3 minus K? Do you thicken the knot?
Yeah, that's right. We consider the tubular neighbor of figure 8 knot and consider the triangulations of complement. So, so in this sense, I mean the knot is on infinity. I mean in the case of ideal tetrahedral vertices is on infinity. So in precise sense, we have a truncated tetrahedral. So to realize how to glue these faces together, we pay attention to this truncated part of this one. So here we have 4 triangles, and we have another 4 triangles. So in gluing faces together, we know we can write a developing map of this triangle. I mean like this one. And we assume the parameters of tetrahedral is W and Z. So if we assume each ideal tetrahedral is parameterized by one complex number, then this alpha, beta, gamma is only labeled by argument of Z. I mean, this is just an argument of Z. And also this one coincides with the argument of 1 minus 1 over Z. Okay, so we know every dihedral angles of each triangles. So in this case, we know we can identify this angle coincides with the argument of W, and here okay, this is a developing map, and this is just a complement of not for one, and I consider the tubular neighborhood. So topologically, a tubular neighborhood is just a torus. So this edge is identified with this one. So this is just a triangulations of surface of tubular neighbor of 4-1 knot. So this edge coincides with this one. Okay, this is pictures of triangulations of figure 8 knot. And this decomposition is first studied by Thurston. And okay, to compute the hyperbolic volume, we must fix the parameter W and Z. So to this purpose, we need conditions for W and Z. And in gluing, I do not explain precisely, but sum of dihedral angle around each edge must be 2 pi. So to fix W and Z, we need consistency conditions. It means that the angle around each edge for each edge, for each edge. So in this case, this vertices coincide with this one, so the product of this one, this 6, must be unity. And also, the product of dihedral angles of 6 dihedral angles must unity. So from this one, okay, I use the conventions of this dihedral angle is denoted by Z prime, and W prime means the dihedral angles around this one. So Z prime is just 1 over 1 minus 3. And this one, so it's same for W prime and W prime. So actually, this is not independent, and from these two equations, we cannot solve W and Z. So we determine the W and Z. We need another conditions called completeness conditions. I mean, the completeness means, roughly speaking, this triangulation is just quadrilateral. I mean, this edge must be parallel to this one. So from these conditions, we obtain W and equal Z. So because this edge is parallel to this one. So W must be equal to Z. So from these equations, we can fix W and Z. And in this case, W and Z is just e to the pi I over 3. Then we obtain the parameterizations of each ideal tetrahedron. The volume of hyperbolic, volume of not complement is given. Here we have 2 tetrahedra, so just a sum of Born-Wigner functions with argument W and Z. And in this case, we have these solutions. So the volume is just 2 times Bloch-Wigner functions. And then this is this is equal to this one. I mean the 2-point. So this is how to compute the hyperbolic volume of knot complement. So we obtain the same values. So we can conclude this volume conjecture is true for figure 8 knot. So from this picture, we just concentrate on the asymptotic behavior. But in recent paper by Zagier, he determined the asymptotic expansions of this Kashaev invariant, and he wrote this, he wrote this type of asymptotic expansion, and he claimed that this coefficient is always rational up to square root of 3. But I don't know how he derived this one, and this is very this seems very interesting functions, but a little bit beyond the mock modular form. So this Zagier called this Kashaev invariant is also quantum modular form, but this seems to be a little bit difficult, than mock modular form. So I want to show some cases which is very resemble with mock modular form.
Can you say what's the connection of this to quantum modular form?
Okay, in the okay, so quantum in this case, quantum modular form is just okay. Sorry. This one, I mean, so the reason is that at the root of unity, at the root of unity, this series coincides with the Kashaev invariant, and Zagier claimed this has a very it will have a very nice asymptotic expansion at the rational value.
Is this this conservative function?
No. Okay, I will explain the concept one. Yeah, later.
Is there supposed to be an analog of ZFQ for every knot?
Pardon?
Is there supposed to be an analog of ZFQ for every knot?
GFQ? Huh?
An analog of C of Q for every knot.
If volume conjecture is true, the asymptotic has a very nice meaning of meaning from the viewpoint of geometry. So the every Kashev invariant could be regarded as quantum modular form.
So
But
there would be quantum modular forms labeled by knots?
Anyway, the definitions of quantum modular form is not very subtle. So.
There's some definition.
Yeah.
But is it related to the volume conjecture, this property of being modular up to some C?
I don't know. But
Is this volume conjecture motivated or connected at all in any way to some kind of ADS-CFT?
please give answer. I don't know.
Is it some semi-classical approximation to Chern-Simons?
Yeah.
Does it follow from semi-classical approximation to Chern-Simons?
Yeah.
This volume conjecture seems to hold if you embed your knot in S3. If, for example, if you consider S3 acted by some discrete group, maybe length spaces, is there any hint what may go on?
Might be, but sorry, I don't know the answer. Okay, so anyway, what I want to say is that the knot is classified into hyperbolic one and non-hyperbolic one. And for one belongs to this class. And as I said, the behavior of Kashev invariant for hyperbolic case is a bit very difficult. In this case, just taking a limit is just simple computations, but to obtain the asymptotic expansions like this one is a little bit different, difficult for this case. So I want to show that much more accessible invariant comes from non-hyperbolic knot case. This case belongs to the most simple example is this one. Trivial knot is belongs to this one, but it is not interesting. So I want to study this case. So the claim is that originally the Kashev invariant is only supposed to be true only for hyperbolic knot. But as I said, this Kashev invariant coincides with the Collard-Jones polynomials, and Collard-Jones polynomials is defined for any knot. So even in the case of non-hyperbolic case, including 3-1, we have Collard-Jones polynomial. So we have such. We can take this type of limit from the explicit form of Kashev invariant. So let's study the case of trefoil. Okay, so this trefoil is labeled like this one. We have 3 crossing and the first knot. Only one knot with 3 crossing. And in this case, we omit details. But we have very nice expressions for this. Trefoil knot. This one. This expression is due to Masbal and Habiro and Ray. So this is very beautiful expressions, and it is difficult to obtain such nice expressions from R matrix. So anyway, in this case, we know.
Could you 1 minus n?
This one?
No, 2 factor. Oh, this is dot.
Sorry. Minus. Thank you. So from this expression, the Kashev invariant is just given by setting Q to the nth root of unity. So in this case, we have large N here. So this term vanish, and we obtain so Kashev invariant for Torefold is essentially given by large F functions, and large F is written by this one. And this is Kontsevich-Zagier series. Contrary to the to a case of figure 8 knot, asymptotics is asymptotic expansion of this large F function is a very beautiful one, and this is also due to Zagier. So I show you a result. I mean, this here Q as just functions of just from this definition, this large F function has no meaning if Q is not nth root of unity, because we have infinite series and Qn is just product. So this expression has no meaning if Q is generic. But if Q is nth root of unity, this function is not infinite series. We have just a finite sum due to at some large n. If small n is larger than large n, this Q product vanishes. So we have a finite sum. So this has a meaning only at nth root of unity. So Zagier claims that if we define phi by this one, here alpha is rational. If we define phi by this one, then he proves So this is, you see that this file has meaning only at rational number. And at the rational number, we have a very beautiful relation. I mean, this is essentially same with the property of mock modular form with weight 3/2. And from this one, we see the shadow. It's just eta function.
And so we should think of half as the weight of the quantum modular form.
Mm-hmm. So this is a very beautiful examples of quantum modular form. So from the viewpoint of volume conjecture, we know in the other asymptotic expansions of large N.
So the limit of this period integral is smooth on the rational axis. Is that the point?
Which one? This one?
Yeah, the right-hand side. So in order to be quantum modular form, it should be continuous on the real axis. Sorry, on the it should be continuous on the real axis.
Yeah, but here alpha is rational one. I mean,
And usually, if you take some arbitrary modular form, you get something which is a distribution on the axis. Here, the claim is that it's not a distribution, but it's a smooth one.
Yeah. Yes. Sorry. Anyway, in the large N limit, this large T, contrary to the moonshine case, this large T is very simple one. Just we have a very simple generating functions of this one. Okay, so if we do not take an absolute value of the Kashaev invariant, we obtain this number. In this case, we have only complex number. This is contrary to the figure 8 case. Figure 8 case is we have a divergence term e to this some number to the large N, but in the figure 8 case, this is just a volume of not complement and just a real number. So the reason is that this trefoil knot is not hyperbolic, and the volume is just 0. And we have from the we know the topological meaning of this one, but we omit. This is just Chan-Simons invariant of trefoil, exterior of complement of trefoil knot, and we know the meaning of this factor. Okay, so my original motivations was to generalize this Kontsevich-Zagier series. And from the viewpoint of this conference, I think we have interest in the quantum invariant, quantum modular form, which has a shadow of eta cube. So we know the answer, and such quantum modular form appear from the quantum Kashev invariant for torus link T24, which is not link. We have two components. We have 4 crossing. And then, in this case, the Kashev invariant. We omit the Colored-Jones polynomials, but Kashev invariant is just okay. We define this one like this. Then my claim is that we have nice modular properties. This psi, function psi, has a nice modular property under the S transformation. This has a weight 3/2, so psi has a weight 1/2. Yeah. So we understand this transformation modular property is essentially same with H functions. I mean the Eguchi, Tachikawa's H functions. Same modular property. I mean, especially we want to say that this psi also has a shadow eta cube.
But psi is not the limit of H on the boundary.
Yeah. The psi is just a function defined on rational number. What is H2? H2.
Does psi have any relation to H of tau?
The function you began your talk with.
In some sense, we can regard as a limit of the H function to the rational number, but I do not have a precise relationship with H tau.
It controls how fast it merges or something?
Pardon? Yeah, but I mean, to derive the modular properties of H, we use the the Ahira integral, like this one appears, and for H tau, we have some dual Ahira integral. I mean, if it is defined on the lower half plane, and this psi is just a limiting value of that dual Ahira integrals as a limit of very roughly speaking, H tau is defined in the upper half plane, and we have another similar functions, not conjugate, another functions H tau, which is defined in the lower half plane, and this psi is just a limit of this H star functions to the rational number. So the M24, I don't know.
T of 2 comma 4, not T of 24.
Okay, so as a generalizations of H functions, Jeff introduced similar generalizations of H functions, and I forget his notations, but I how to write K. I mean the K equal one case is M24, and so as a generalizations of this correspondence between H and psi, we know generalizations of this torus. I mean, they just study the torus link. And in this case, the shadow is in your notations, right? Okay. K plus 1. Oh, sorry, I'm not sure, but yes, similar one. I mean here.
But you don't have any restriction on K from your side, from the torus, right? K can be anything.
Pardon, torus, not case? Eh?
I can take K to take any.
Yeah, anyone, but yeah. Yeah, sorry, singular case, but I mean the mock theta function which appears from the C to the 6 times K case. We have infinite series. If we ignore moonshine phenomena, we have we can define such mock theta functions from the character decompositions of higher dimensional cases. So anyway, so here I mean we have a vector varied version of this psi. I mean and the modular S transform is like 1, like this. And we have then we obtain this kind of transformations. So the claim of this correspondence is that the only one component of this vector valued quantum modular form coincides with the Kashaev invariant of this one. And I do not know the meaning of topological meaning of remaining element.
Is it the first component, the one that
first component. First component coincides with the Kashaev invariant. Okay, so so here I want to say not only the moonshine phenomena, but the from the viewpoint of quantum invariant modular, mock modular and quantum modular form is very interesting to me. So anyway, thank you for attention.
Questions?
is there some ADE classification of these courses?
Sorry, I don't know.
No, it's a serious question.
Sorry, I don't know.
What
ADE
what
of
specifies this class of knots? The knots labeled T2, 2k plus 2. What specifies them amongst all possible knots?
This is just a torus case. So from the viewpoint of hyperbolic geometry, this type of knot is not interesting. Just a fibering knot. And sorry, I don't know how to connect, how to relate this torus link with AD classification and something like that. But in this case, I only consider the special point of Carado-Jones polynomial, which has gauge group SU2 with n-dimensional representation. So it might be interesting to study the other gauge groups. And such work, recently I think string theorists has interest in such SUN, not invariant, which comes from SUN gauge group, but they only study the categorifications or something like that, and I think the asymptotic studies on asymptotic behavior is missing, I think. So if you have any idea, please let me know. I'm very happy to hear.
What happens if k crosses, I mean, Leibniz values goes to 8, right?
No.
This here I can have a knot which will take any k, right?
Yeah, any k.
So
Yeah.
what would be the shadow in the other cases?
Yeah. The shadow is defined for all k.
There's no problem with the shadow. The thing that happened.
Okay, then thank you very much again.